Hi everyone, welcome to my presentation. In this video, we will explore the introduction of mechanical waves, delving into their types and the principles of their behaviors. Let's start with the definition. Mechanical waves are disturbances that transfer energy through a medium, such as solid, liquid, or gas, without transporting matter. These waves rely on the interaction between particles within the medium of energy propagation. In the mechanical waves, particles of the medium oscillate around their equilibrium positions. The direction of the oscillation will determine the wave type. Unlike electromagnetic waves, for example, the microwaves that used for cooking food, the X-rays used in medical imaging and security. Mechanical waves require a material medium to move, so they cannot travel in a vacuum. Mechanical waves have several key properties. First, wavelength means the distance between two consecutive points in a phase. Frequency means the number of wave circles passing a point per second. Amplitude is the maximum displacement of particles from their equilibrium position. Wave speed is the rate at which the wave propagates through the medium. Period is the time for one complete wave circle. After that, let's have a look at the three types waves of the mechanical waves. The first one is a transverse wave. A transverse wave is a type of wave where the particles of the medium move perpendicular to the direction of the wave's propagation. Imagine a rope being shaken up and down. The wave travels horizontally while the rope's particles oscillate vertically. One of the good examples is when wind blows over the sea surface. It transfers energy to water, causing the surface to move in a wave-like motion. In this case, the particles of water move up and down in response to the energy transferred by the wind, while the wave itself moves horizontally. Next, consider waves on a string, such as those on a guitar or violin string. When plucked or bowed, the string vibrates. The oscillation of the string is perpendicular to its length, exemplifying the transverse behavior. Secondly, we have longitudinal waves, which are waves in which the particle displacement is parallel to the direction of wave propagation. The example of sound waves are when sound produced, it creates oscillations in air molecules. The energy of the sound wave moves forward, while the air molecules oscillate back and forth in the same direction as the wave. The wavelength in a longitudinal wave is the distance between two consecutive compressions or rarefactions. Also, compressions means the regions of higher pressures, where particles are densely packed. Rarefactions are regions of lower pressures, where particles are spread out. After that, we have the surface wave. A surface wave is a combination of a transverse wave and a longitudinal wave. When a rock hits the surface of a pond, it creates a disturbance. These waves travel along the water surface, with the energy moving outward, while the water molecule is moving in a circular motion. Finally, we have the Doppler effect. Doppler effect is the change in frequency or wavelength of a wave as observed by someone who is moving relative to the source of the wave. When a wave source moves towards an observer, the wave compressed, resulting in higher frequency or shorter wavelengths. Conversely, as the source moves away, the wave stretch, leading to a lower frequency or longer wavelength.